All right. I think we're starting to get more people, and I assume a few more are going to trickle in. So I'm going to plan on starting my introduction and brief presentation at about five after. So for now, we're just going to wait for a few minutes. People can socialize however they choose while we're waiting. I'm going to post a link to my slides in the chat. Link. So everybody has an understanding of what we're going to be talking about today. Yeah. Okay, so we are approaching five after. People might still end up trickling in, but I think now is a pretty decent time to start. So I'm going to do a brief introduction of the forum and of myself. And then I'm just going to get into presenting on alternative compute frameworks in R. So I'm Nicholas Cooley. I am the new developer engagement lead for Bioconductor. I'm funded under an EOS grant from CZI, and my purview is basically things like managing the developer forum, managing the champions program, and developer engagement events. So we are going to be hosting a hackathon attached to the Turku Euro Bioconductor meeting in June, the beginning of June. And we are going to start planning some others here soon. So I thought that presenting at the first reincarnation of the developer forum would be a good thing so that other people didn't have to sort of guess as to what we were going to be starting with. So I'm going to be talking a little bit about alternative compute frameworks in R, partially because they're very important and partially because they're not there just aren't very many ways to access CUDA or openCL or Metal or any of these other ways that we do compute on discrete memory devices or hardware accelerators. So that is my intro. That's the forum intro. And with that, I'm just going to get started. I need to share my screen, which is here, and uh, Chrome. I'll share that window. And I believe I will still be able to manage the waiting room in case people join while I'm doing this. Okay. All right. So alternative compute frameworks in R. We're going to start from the beginning. So um, what are frameworks? Oh, good. That pops up right there.
Nick, do
Okay.
you want to go to slideshow or presenter
Uh,
mode?
oh, thank you. Yeah,
Yeah.
perfect. All right. All right. So, starting from the beginning, framework is just the verbiage we use for the sort of OS level tools to access things that aren't already part of the OS. In this case, this is hardware accelerators or alternative compute devices. This is typically GPUs, but not necessarily GPUs. Google is making a push at making tensor processing units a thing. Hardware is always evolving. We don't know what the future is really going to look like for some of these devices, but alternative compute resources besides CPUs are likely going to become a bit more common and become a bit more heterogeneous as we move forward, as hardware evolves. So um, these frameworks give us tools to access these devices. So there's a heterogeneous landscape of who provides these devices. Everybody typically knows NVIDIA and AMD. Those are the major providers. Apple now has their own hardware setup with metal devices. There are others, but those are basically the three major players at this point. And the tools that we use to access them, NVIDIA has CUDA. CUDA sort of ate everybody's lunch. AMD used to use a framework called MROC. It sort of has dissipated, and I think it's actually completely deprecated now. Um, there are open source frameworks like openCL, which is sort of how I got into this. There's an openCLR package that is pretty nice. It's a little inflexible, but it's a tough problem to solve, and I don't think the maintainer spends an enormous amount of time working on it. Um, and then Metal is how Apple accesses um, the discrete GPUs that used to exist on that do exist on the legacy MacBook Pros. Those were, I believe, almost completely AMD devices, and it's how they now access their dual architecture silicon devices. So if you have an M3 or greater, you are going to have a dual CPU GPU setup, and the CPU setup is actually pretty complicated too. It has heterogeneous cores within the CPU. Um, openCL, which is a cross-platform framework, is entirely accessible in C. So as long as you can get the C headers, which you can get through Homebrew or your favorite package manager. You can do OpenCL compute on your Mac. You can do it on enterprise level hardware. You can do it on your gaming PC or whatever you're using. OpenCL should be able to access. OpenCL has tools to access basically any vendor's hardware. It's run by the Cronus Group. It's open source. It's quite nice. CUDA, as I think probably most people know, is hardware locked to NVIDIA. I believe that AMD hardware now supports CUDA, although I don't know if it plays well with it. And then Apple is locked to both Apple OSs and Apple hardware. So if we want to access these frameworks, we typically are going to have to do this through rs.call or .external interfaces. Um, and for OpenCL and CUDA, this means that we have to have C functions that we can call to do things like device discovery or buffer management or what have you. For Metal, this means that we have to do this in Objective-C because that's what they chose. Um, so if you want to work with Metal, which I've been fiddling around with, you have to write a mix of Objective-C and C code to access the GPU through R. So that's a pretty brief introduction of this. It's very non-exhaustive. This landscape is used to be a lot more heterogeneous. It's sort of coalescing into sort of major manufacturers and suppliers at this point. Um, whoops, that's not what I meant to do. Uh, why is that should be fine. Um, oh boy. Okay. there we go. Sorry. So what's present in R now? This is a bit of a graveyard of work that people have put in and then abandoned for a variety of reasons. It is not trivial to access these APIs and to manage passing data between compute layers. OpenCL has existed for quite a while. It is great for prototyping. It's great for looking at sort of what your non-CPU compute devices are capable of, but it is a little inflexible. It's not under active development. And like I said, this is not trivial work, so I'm not going to try and cast aspersions on anything. It works, it's inflexible. That's what it is. There's a variety of things that have existed in the past and are no longer on CRAN or appear to be relatively abandoned. I just learned about this RVNSCL thing about a few days ago as I was double checking things for the presentation. There were various CUDA focused packages that were on CRAN for a while and are no longer on CRAN. Posit has tried to build out a torch-based package that is a wrapper for libtorch, but not PyTorch. And this, I believe, is NVIDIA focused. I do not believe it works on other hardwares, but other people can check me on that. And again, that's a Posit product, so there is at least some effort behind supporting that. And there are others. There have been plenty of attempts to do GPU compute in R. It's tough, and this sort of that's the way it goes. All right. So what do they do briefly? So your machine typically has a CPU and all this other hardware, and most laptops have some fairly small discrete GPUs to do graphic stuff for the screen. That has changed over time as we've gotten better at building processors. Um, but big desktops and enterprise level hardware have discrete GPUs, and these are processing units with reduced instruction sets that typically have very large onboard memory, and they are designed to do specific sets of instructions very, very quickly. So if your CPU is capable of, some library of actions, your GPU is capable of doing a much smaller library of actions, but its advantage is that it has more cores to do those. So instead of doing, 1,000 things on 12 cores, you're doing like 50 things on 1,000 cores or something like that. Um, and to get to that, we have to basically be able to identify what that device is. So we have to have system tools to go out and say, there's this device here. It's connected through my system by PCIe or whatever, right? We have to manage execution on that device. So does the device use language similar to the CPU or dissimilar to the CPU? Is compiled code the same or very different or what have you, right? We have to manage data transfer to the device. Most of these are discrete GPUs. Most of these have their own discrete memory. That's not the case on the Apple M3 and M4s. They have unified memory, but for the most part, it's discrete. So that means we have to know how to transfer data from our on-byte memory and maybe even our cache or disk to the discrete memory on the GPU. And that means to some extent we need to know what data types are supported in those two places and how to transform them if they need to be transformed. And then we need to manage execution on the device. Does the device have a similar language or a dissimilar language to the CPU? How do we know when execution starts or ends? How do we know how to manage how data lives in the discrete memory on the device? How do we know how threads are doing things? How do we communicate information back to the OS? Um, and those are all the things that the frameworks manage for us. So CUDA, openCL, Metal, they all have accessor tools for saying, this is how I build a function. This is how I build a function execution pipeline. And this is how I send my data to the device. This is how I send my data back. And the frameworks all do that for us. Um, that's the general conceptual picture. A bit more specifically, what this looks like is, on the CPU, we have sort of a narrower set of tasks, and this set of tasks is sort of narrower because the OS does a whole lot of different things for us. So the OS is doing a bunch of work in the background to make our life simpler. And we don't necessarily have tools on the GPU side to make our life simple. So we have to go through a bit more rigmarole to get what we want. Um, yeah, there are some steps that are shared, some steps that are different, and the steps that are different are typically things that the OS would handle for us on the CPU. Um, yeah, there's not much else to say there. So if we want to leverage GPUs or other hardware accelerators, how big are the improvements? When do they show up? So an example I wanted to use for this is matrix multiplication, particularly a naive implementation of matrix multiplication. So the code that you see on the left is an openCL kernel to do very naive matrix multiplication. And this would be very much blown out of the water by something that's optimized. This is meant to be an example. And you can see that for smaller object sizes and the plot on the right, that the R's internal R's internal applic or internal implementation of matrix multiplication basically does on par or better with either OpenMP, which is how we do multi-threading on the CPU. Typically, there are other ways to do it, but this is sort of the open source accepted way to do it. And then we can have an OpenCL implementation, which is the code you see on the left, and doing this with Metal, which is also not present. So OpenCL and Metal are the two GPU implementations here. Um, OpenMP is a CPU implementation that is one of them is naive, one of them is a bit more optimized. And you can see that it takes to about 250, a dim size of 250 integers for you to start seeing um, kind of large improvements over uh, the internal implementation of matrix multiplication. So this is sort of what you're looking at. And the reason I choose this is that the reason I chose this is that um, this is about the inflection point that you need to get to start seeing improvements on the GPU. So there are data transfer overhead considerations that you will typically find very simple operations will end up being slower on a GPU if you're not careful. So um, there are management considerations to what you choose to do on a GPU and what you choose not to do. Uh, so that's what's possible. Matrix multiplication is sort of the start of where you get advancements. Um, as you start to pursue problems that are much more complicated, you will start to see bigger improvements, and that's the sort of that's the goal, right? That's why everybody does all their machine learning on GPUs because they can do lots of simple things very, very quickly. Um, so why did I want to give this talk? Partially because we can't it's hard to find implement it's hard to find ways to interact with the GPU in R. I'd like to encourage more people to do it. I'm fiddling around with Metal myself, but the OpenCL package is sat there largely intermittently maintained for a long time, and it could be very, very useful. Um, and this is sort of a bit of an advertising pitch, but if we want to pursue work where we make frameworks accessible in R, we should be pursuing this like infrastructure. So sort of the bullet points on the left are, how should we be thinking about incorporating code that does this? And this code snippet on the right is like is sort of the idea that the packages that have existed on CRAN, people have put a lot of work into them and then they've disappeared. And part of the reason they've disappeared is that because they're difficult to maintain, or maybe they're too situational. And if we can build more fundamental tools that allow people to develop, I appear to have lost my speakers, but I think that's okay for now. Uh,
Sounds
Yeah, we
good
can hear
to
you.
us. Yep.
okay. Um, I think, yes, everything's back. Okay. So, um, the idea here is that we should be pursuing these frameworks like infrastructure. Um, if we want to make something that's going to last, we can't make the most uh, attractive thing first. We've got to make things that are going to be reliable in the long term. Um, and then that's pretty much the end. So this was a pretty brief talk. I included links to the to Simon Urbanic's openCL package. It's been around for quite a while. He maintains it on and off, it looks like. It had some updates recently because it stopped passing checks on CRAN due to, I think, changes in openCL's headers. Um, I've been working a bit on metal packages recently. None of this is particularly official, but I put the work in. Um, And that's largely it. So the goal here is to try and get people to start talking about these topics. And I don't know, maybe other people will be interested in working on them as well. But I'm also interested in hearing sort of feedback about what people think. Are you happy with what frameworks are accessible in R? Do you prefer to just do all of your hardware compute in Python? I mean, these are things that we want to hear back from the developer community about at the end of the day. So I'm going to stop sharing my screen and there's a chat message. What compiler was used in these tests? So those tests were all on my local machine, which is a Apple M4. Um, OpenCL has its own compiler. Metal has its own compiler, and they compile the functions that get sent to the devices. So I don't know if that's necessarily the answer that you're looking for, but yeah. All right. I don't, I believe that people can unmute themselves. If they can't, someone please let me know. Um,
Yeah, I'm unmuted myself. So
okay. All right.
thanks a lot. I think this was a very helpful talk. And I particularly like this notion that we had better help people maintain the interfaces that they started to devise.
Yeah.
Of course, we have to have the right use cases so that it adds value to us. And I guess the way that I've been using GPU hardware is mostly through torch dependent software like TensorQTL.
Yep.
Um, and there you are, we're just using reticulate, let's say, to call the Python stuff, and it all seems to work pretty nicely. So I don't feel there's a huge loss to, reusing working software in that way, but helping people to devise, tools that we, you know, usually the Python tools are evolving on their own, oftentimes in ways that lead to complicated dependency configurations. And so getting our hands on, let's say, the LibTorch interfaces from Posit, which I had a feeling have not been kept up. Do you know whether they are actively maintaining that?
I really don't know. I know that so about a year ago I fiddled around with our torch and it felt very slow and clunky at the time. Um, I don't imagine that. people aren't maintaining libtorch. It's the underlying code to
Yeah,
PyTorch.
yeah,
I can't imagine that people are just letting that, you know, rot,
right. Yeah,
but who knows? Um, I think that the one of the reasons that I pursued this at the very beginning was I spent a long time working on some projects doing structure prediction from sequence. So I was using the evolutionary scale model stuff from what at one time was a Facebook research group that spun off into their own company that was just then bought again by Facebook, which is a very interesting sort of history. But having to do everything in Python there felt very circuitous, considering that at the end of the day, they're just calling libraries into or sorry, they're just calling these kernel functions into the NVIDIA CUDA API, right? It's just wrappers for the CUDA API. And if it's just wrappers for the CUDA API, we can do that too. And we can maybe do ones that are a bit better for our use cases than, we get from, implementing reticulate, which is a massive piece of work and does work, but sometimes feels quite brittle.
yeah, fair enough. I see that Alexei doesn't have a mic, but he did pose a question in the chat.
Yeah. I think I'm not entirely sure what you're trying to say, but the to interact with openCL, you do need to be doing this in C initially. I don't know if openCL has a C++ API. I know they have a C API. Um, but you have to, but that's the layer that you have to use to get to the API. So you have objects in R, you can do compute in R that typically is um, optimized depending on who wrote it and when and how critical it is, um, as one does for OpenMP. Um, OpenMP is an additional library for C. OpenCL is very C-like. I'm sorry, I'm not sure I quite get what your question is, but um, most of the languages for kernel functions appear very C-like. CUDA is based on C and C++. I believe Metal is based on C++ as well. So when you get to writing your kernel functions, they are C-like. Um, I think that answers your question, but I'm not entirely sure it does. So please feel free to reach out to me about it later if you want. Um, but yeah,
I guess the flavor I'm getting from Alexei's question is that on the one hand, one can think of a package like openCL and try to maintain that. On the other hand, one could say, well, as a package developer, I can do it all myself for the purpose of my package. That there's enough interfacing capabilities through RCPP or the dot call that I could just manage that myself. And certainly there may be examples of that already. I don't know. Um, but, you know, people vote with their feet, I guess. If
they
you did a
do.
good job of layering this, then you'd have more users that didn't have to do it themselves. I see Parikshit had a question there, which is sort of strategic. So why not read that one out?
It's not very clear on the goal. The goal is not to shield people from the complexities. The goal is to convince people that it's worth it to have infrastructure packages that do this. So if R or Bioconductor had a mature and reliable package that gave us successors to the NVIDIA API or the Metal API or the OpenCL API, um, people would just need to know how to write out their kernel functions, which they're largely already doing in R. So that just becomes a question of learning how to write out your math in a different language. And then you could just deploy that to whatever device or framework you are trying to use at that point. I think that's does that answer your question there?
I would hope folks can just sort of unmute themselves and have a conversation. There's no need to
Oh,
do this
sorry.
through the chat.
Yeah, yeah.
Go
Yeah, no,
ahead.
thank you. I think that's very helpful. I really like that idea because I think some of the, like as a developer, uh, there are like I guess there are libraries of functions that you might think of wanting to use for your GPU. Like
Yeah.
there's kind of a lot of decisions that implicitly go into that, like, the data layout problem and trying to have fused kernels and trying to compose your calculation in particular ways and try things out because there's just parts of there's things that are just not visible, right? And you have this
Yes.
sort of theoretical model that you're assuming that the hardware is running. And I think this is great because this is something that you'd have to do in any case, just to have a ground truth of like how well is my code performing, with using the vendors sort of tooling. So uh and I think that's like a very good stepping stone. If one were to try and use, more off the shelf tools, then at least you have this sort of performance tests that you could compare against. It's like, well, um, are all these benefits, like, is this an okay loss of performance in order to have like, lesser maintenance burden and so on.
I mean, I think that, once you get accessors to the API that are reliable and robust, I don't imagine that you're really going to be seeing any loss of performance. Like the overhead to call and external is not large. I mean, um, hold on, let me share this again. So I think you're looking at my um, so so the plot on the right, the reason that openCL performs so poorly at the smallest dimension size for matrices is because openCL is performing just-in-time compilation, and that's it. That all of that difference you see between openCL and Metal at that dimension size is the time difference of just-in-time compilation. The Metal kernels are compiled ahead of time, and everything goes smoothly. And then once you get past that, you can see that they basically kind of overlap beyond that. But your performance hits aren't going to be you're not I don't think you're going to take a performance hit unless you've written the accessors poorly and you've done something like maybe managed your data transfer inappropriately, or you're duplicating things where you shouldn't be, or whatever, right? Um yeah, sorry, that's a bit of a tangent, but I hope that sort of answers your question.
Yeah,
Stop
yes,
sharing.
thank you.
Yeah.
This is a somewhat naive question. Are there some analysis or operations that lend themselves well to GPU or not?
Um Basically, I guess to touch both on that, and I think uh, Parasheet's one of his points earlier is that um, in any place that you can ensure that so GPUs are really going to shine anytime you can send a block of data to them, and you can do multiple things on them at once before you send your data back to the host memory. So he mentioned fused kernels, and this is sort of a place where my understanding is every implementation of GPU access in R has just stopped. So openCL doesn't support fused kernels. Um, to my knowledge, nothing else does either, and that is a big point to think about. it's complicated to write code that support that, and figuring that out is probably not trivial. But yeah, if you can send some single origin piece to your discrete memory and then do a bunch of operations on it and then send it back after those operations, that's where your GPU is going to shine the best. Um, you know, anything from matrix multiplication to that is still going to have considerable performance improvements. Anything less complicated than matrix multiplication is probably not going to see considerable performance improvements. Formalizing hardware support. Sorry, the question
Yeah,
in the
so
chat. Yeah, go ahead.
I can also speak it out. So
Yeah.
I guess one of the complexities with also using the vendor libraries is you have to think about what hardware to support, right? Maybe Apple is like a relatively easier sort of system because there's only, so many versions that you have to think about. And um, I I don't think I think you can kind of get this, like what a lot of people do. I think they get the Mac Minis, to test on, and those are relatively inexpensive, and you can test on a wide variety of devices. But I'm just thinking like this is like, there are just lots of devices, right? And there's a lot of library versions, and I'm just thinking it might be good to at least be explicit with these CUDA versions or these metal versions, and these hardwares are sort of, or these minimum RAM amounts, or at least as a developer, when you think about performance, try to think about it running well on these platforms.
Great question. And we've done a little bit of work in that direction. I don't know if you've run into it, Parikshit, but maybe I'll share a screen for just a minute or two to see where we are, because I don't know exactly. Now, let's see. I don't seem to have a share button right now.
Do
Uh,
I?
I
I
had
think Zoom
one
made a change to where you have to be more explicit about giving
a
shared
moment
permission.
ago. I had one. But anyway, yeah, here we go. Share. All right, here. Because I know where I'm going, right? Share screen. So you should see something on stable HLO right now, which is not relevant yet. Is that right?
Yes, we see that.
I'm
Yeah.
not the greatest Zoom user. You have to bear with me. Let me see if I can move this down a little bit, and then we'll visit bioconductor for a minute, and you can see, okay, I'm okay with this. Let's go over to bioconductor. Come on, my friend. All right. Bioconductor.org. We'll hide this little guy here. I don't know if you're seeing it. And then come on down over to the build reports. And yes, we have a special little guy here, GPU software builds. And we have some friends on the call who have made an orthos package. We had our bowtie CUDA, and then SCVIR, which I have deprecated because it depends on something which I haven't really been able to keep up with. So we did take a couple of GPUs that maybe you can find out exactly what GPU it is somewhere here. There we go. That's important, right? You need to be able to see exactly what's going on. And this idea of introspection, I think, is just so under played in our world, where you really want this thing to be able to tell you what it is doing and how it is doing it. And we need to do a lot more of that. And that's a developer forum topic for the future. May not take a whole half hour, but it's something where we really need to be able to expose it. So let's see what we got here. A100X 10C running CUDA 12.2. And then this other machine here is an L40S running CUDA 12.9. Do we expect the same things for these? Well, I guess not. I hope this starts to answer your question, Parikshit. We have tried. And one of the things that was going on with SCVIR, you may know the symbol MPS for the metal performance shading. And Torch knows about that device also. And so even on our Mac builds, I did have a little bit of introspection saying, okay, this event used the MPS versus the GPU, which you would see on one of these systems here. So we do have the ability to reach out if the developer wants to exploit a GPU. We have some hardware for that. And as I've shown you, we have a couple of software configurations. And it's even more than we describe here because on the Apple machines, we can also use MPS. So there's a lot there that can be taken advantage of. And I think one of the things the developer forum wants to do is to let people know that if you learn how to do this, we'll be able to give you, support for it. I'll shut up for a couple of minutes.
Yeah, no,
Yeah, I
that's super
think
helpful.
it's
Thank you.
yeah, I think that's a that's a great point, and I think that part of the like where you see the error between the two different CUDA versions is one of the reasons people turn to openCL sort of outside of sort of regular context because openCL hypothetically is managing those vendor versions. So you may not be as fast on an NVIDIA device with openCL, but in the background, the Kronos group is trying to manage those drivers and interactions with them for you. And that's the selling point of something like that. Whether that's acceptable or appropriate or the best choice, I have no idea. But that is what they try and focus on.
Yeah. So maybe I'll share one more time so we can look at stable HLO just for a minute. I don't know if you've heard of it. I learned about it by a person who is heavily involved now with bioconductor and GPUs. It's Gabriele Celes, who's out at Padova. And he is, I think, working on our interfaces to this. So I guess the idea is it's at a little higher level, right? HL means higher level here. And the high level operations for machine learning are supposed to be defined in a way that you can take advantage of these well-known software stacks and get a lot of benefits, fully specified compatibility, 5 years backwards, 2 years forward, and so on. This idea is very attractive to me. I haven't had any time to deal with it. I especially thought that I'd really like to learn how to use JAX to define statistical algorithms, and I have never been able to open up the bandwidth to go back there and do that. These are other things that I think could fit into developer forum topics. And I think they should be on the radar screen of people who are developing things that are going to have machine learning touch points.
Yeah, I've talked with stable HLO, or I've talked with some folks about stable HLO, and one of the critiques I've heard a few times is there's worry that because it's a Google product, it could just vaporize the way other Google products have in the past. I mean, it does appear very attractive. There is no doubt about that, but that is a thing to consider.
Yep.
Yep, if I may add or repeat some things. Yeah, I think working with GPUs is becoming more and more routinary overall for we are talking about nowadays with this huge data, single cell transcriptomics image is getting more and more common the use of those kind of hardware, and I think it's a necessary evil to figure out how to mix the simplicity to access to those GPUs to the R community, even because one of the things I am paying attention is how the Python community is taking the whole credits working with deep learning models for biology. And I think in what point R should be capable of that. We will establish if there is biologists interested to create a new deep learning model for something, and of course if that pure person need to train a lot of data, they need to work with GPUs. And even though if R is not consistent in that, then they will force to move to Python. And I think that is not the case because R is a solid programming language capable of those kind of things. And as well, yeah, my I have not real long experience with GPUs more than working. I have worked with PyTorch geometric, if you know that, is for graph learning. Uh, yeah, this is it could be yeah a nightmare sometimes because that depends of which GPU you have and if this is the license, the drivers, and if the version of the package you are using is compatible with this version of CUDA you have and so on, but someone have to do it. It's like someone have to put hands on the ground and just start doing that. And I think even starting with baby steps, I think one of the major power of bioconductor is this community based, this you can have a problem and you have those vignette going step by step what you have to do. And I think starting with that is just the very first step. For example, the very first question is my computer recognizing my GPU? Yes, no. How to do it? Probably that is the very first step. We can just start to do it, creating this community based on those kind of stuff, then just moving up to the next level, how to do minimal implementation, for example, openCL and R, then you can have this Choi example and say, if you are running this Choi example within R, if you are having these results, your GPU is working as basically expected or not. Otherwise, it's like, okay, you have a problem, then how to solve that problem, those kind of things. I don't know, probably I am over verbalizing myself. Sorry for that. But I think, yeah, I think this is a natural step. And yeah.
Yeah, thank you for that. I just wanted to see whether our friends from Basel who have the Orthos package have any comments on whether our GPU framework, which only has 3 packages evidently, has been helpful, and whether we should be inviting other contributors, maybe even from your own groups. That would be for Charlotte or Michael.
Do you want to take this, Charlotte, or do you want me to maybe start?
Feel free to start. I'm trying to.
So the main developer of Orthos, Panagiotis, is unfortunately not here, so I cannot speak for him. And I think it was definitely useful to be able to run this to see how it works. It would be especially useful if there were also different backends and different types of GPU or TPUs available, because that's I agree with what has been said before. I think this landscape of the hardware is getting more and more complex. And that is, for a developer, poses at least 2 problems. One is that we may not have all these types of hardware available to us so that we can test if our code runs there. And the second problem is one that maybe could be solved with an abstraction layer, which is that ideally I want to write my code once and then hopefully it would run on multiple backends. And I think that's the great power of some of these Python frameworks that exist for machine learning, that I can define my model in Keras or PyTorch, and I do not have to worry about the hardware backend, and it will be useful for anyone who has any one of these supported backends. So I don't know if we can get there, but I think that would be like my wish if I could name one as a developer.
Yeah, I agree. I mean, I think it is really helpful to have the ability to test packages on different backends. I think the problem we ran into was that I think more of a configuration issue, probably with the drivers, the CUDA drivers or something like that. That turned out to be a bit hard to troubleshoot on the builders.
Yeah.
So I mean, that's also a complication that is not really built into the package, right? It needs to be able to interact with what's installed on the system.
Yeah. Yeah, so we try to be as explicit as we can about what that system is and when to update drivers and what it's going to break. I think we have not got any systematic control over. Alex, I don't think has come on, but Alex has built containers with certain NVIDIA. It might even be able to do multi-layer, so that there are several stacks of software for different drivers, so that you can get the right one in the container to match the one on the hardware. So these are topics that I think it'd be nice to have a little subgroup on to make sure that our tooling gets to where it could be to meet those sorts of requirements. But I'm going to shut up now. Nick, your thoughts are welcome.
I muted myself to try and be polite, and then I forgot to unmute myself. Yeah, my one of my impressions of the driver problem in Python is largely that because Python sometimes can be fairly loosey-goosey with its versioning, it's very easy to have different tooling that requires so many different drivers, and I think that can be a place where Bioconductor specifically, and maybe R generally as well, can enforce sort of the monolithic versioning that gets enforced in R and sort of circumvent that problem. And I mean, whether that's good or bad, I don't really know, but it certainly is a potential.
Yeah, I think it's worth pointing out that the whole build system has been a very flexible and adaptable creation because we started it before any type of CI was available. So it had to, do everything that bioconductors needed. And now we're transitioning over towards our universe to manage the creation of binaries, the checking on multiple platforms, and so on. A very GitHub action oriented technology where we've discussed the idea that, we do think that there's going to be more GPU usage in bioconductor. Could the build system in our universe also accommodate GPUs? It's not natively in GitHub Actions, as far as I know, except in a very limited way. And so the idea of a hybrid build system, one in which the bulk of what goes on in software package processing is done in our universe, but there's this other little nook and cranny where the GPU that we have invested in can be used to do some additional testing. That I think that's going to be a reality, but it's not going to be something that our universe is going to take care of for us. So we have to do the plumbing to make sure that the data gets over to the GPU or the software gets to the GPU and the test results go back to some coherent place. So that's just to put on the radar screen that these transitions and this, ever increasing spectrum of combinatorics of test platforms is not we're going to try to keep that going, but it is not completely straightforward. So I think the more voice we can get for people who are interested in this and find it important for their genomics, the better we can do in trying to get support for the integrated, coherent testing and performance evaluations that Bioconductor can do.
One thing we have seen in the Zulip, there is a channel for GPUs. They are in a specific project, as far as I know. They are dedicated to that, but I don't know if you contact some of them, David, for example, because looks like they have, mm, well, a bit more dedicated energy to that. I don't know if they can, or if you have contact them to provide some good feedback.
Yeah, so you're talking about the Zulip channel on GPUs for Bioconductor. Is that right? Yeah. So I welcome someone to propose a working group for the technical advisory board in Bioconductor to help establish an agenda. And they can communicate through the Zulip channel. As you mentioned, they can start new conversations there. But the idea would be that we need a small core of individuals who are going to work on this in a consistent way. And they'll be recognized because they can come to the technical advisory board and report on their results. That's a process in the technical advisory board. So I would hope that that makes sense to you. And if you feel like taking a leadership role there, that would be quite welcome.
Thanks, Pep. I will initiate the conversation then.
Great.
So we are about 2 minutes out from the hour, and this is only scheduled to till the hour. So does anybody have any last thoughts they want to contribute before we close the meeting and sign off?
Well, I just want to thank you for doing the first one and managing this renaissance. And how often is this going to happen?
It is currently scheduled for, we're trying to schedule it for the last Thursday of every month at what is currently 4 p.m. GMT. I'm pretty sure Ireland does daylight savings time,
Okay.
so I don't know when that changes, but
Yeah. Well, thanks once again, and thanks everybody for coming. I think you did a great job, and I hope we can get that little group going and then talk about something else next time. You can help decide what it is.
yeah, we are actively recruiting people to contribute to further developer forums as well. So if you have something you want to talk about, just email me.
Please do. Yeah, great.
Yep.
Thanks a lot. We'll see you.
Thanks, everybody.
Thanks. Bye.